you ever wondered how birds, especially homing pigeons, manage to find their way home across vast and unfamiliar distances? Scientists have long been fascinated by this remarkable ability. Today we'll explore the navigational system of birds, uncovering the mechanisms and strategies that allow them to travel hundreds, even thousands of kilometers with astonishing accuracy. From magnetic compasses to mental maps, birds employ a sophisticated toolkit for orientation. In this video, we'll break down the science behind their journeys, starting with the basics of how birds use external references to set their course. Let's embark on this journey into the world of avian navigation. Birds rarely have direct contact with their destination, so they rely on external references to orient themselves. The two main cues they use are the geomagnetic field and celestial signals, such as the sun. These cues are accessible from almost anywhere, making them ideal for long-distance travel. For instance, homing pigeons use both a magnetic compass and a sun compass. The sun compass is learned and relies on the bird's internal clock to compensate for the sun's movement, while the magnetic compass is innate. If the sun is hidden by clouds, birds seamlessly switch to their magnetic compass, ensuring they can always find their way. Foundational theory for bird navigation is the map and compass model, first proposed by G. Kramer. According to this model, birds determine the compass direction to their goal and then use their compass to follow that course. Experiments such as clock-shifting pigeons' internal clocks show that birds rely on their sun compass, as shifting the clock causes predictable changes in their orientation. This model has been confirmed across various distances and locations, demonstrating that birds consistently use an external reference to establish their home direction, rather than relying solely on familiar landmarks or internal cues. When birds are young and inexperienced, their navigation relies heavily on information gathered during their outward journey. For example, if young pigeons are displaced in a distorted magnetic field, they become disoriented, showing that they depend on magnetic cues to record their route. This strategy, known as route reversal, involves remembering the direction traveled and simply revering it to head home. However, as birds mature and gain experience, they shift away from this strategy, relying less on the outward journey and more on information available at the release site. This transition marks a key development in their navigational abilities. As birds gain experience, they develop mental maps that allow them to navigate using site-specific information. These maps are directionally oriented representations of the environment, incorporating both landmarks and environmental gradients. The grid map concept suggests that birds use at least two environmental gradients, such as magnetic or gravitational cues, to determine their position relative to home. By comparing local values with those remembered from home, birds can accurately set their course. This system explains why pigeons can head directly home from unfamiliar locations, even when deprived of outward journey information. Close to their home, birds rely on a mosaic map, a mental representation of prominent local features and landmarks. This map is built from direct experience and helps birds navigate when environmental gradients are too subtle to detect. The mosaic map includes visual cues and possibly other sensory information, such as sounds or magnetic anomalies. Unlike the grid map, the mosaic map cannot be extrapolated to unfamiliar areas, but it provides precise guidance within the familiar terrain. This dual system of grid and mosaic maps ensures birds can navigate both near and far from home. Development of a bird's navigational system is a gradual process that begins with innate abilities and is refined through learning. Young birds start with a magnetic compass, but as they venture further from home, they learn to incorporate landmarks and environmental gradients into their mental maps. Free flights and exploratory journeys are crucial for gathering the necessary information. Over time, birds continuously update their maps with new experiences, ensuring their navigation remains accurate even as they encounter new regions. This learning process is flexible and ongoing, adapting to changes in the environment. Birds' navigational maps are not static, they are continuously updated as birds gain new experiences. Even adult pigeons with years of experience improve their orientation when they become familiar with new regions. Training programs that expose young pigeons to various release sites help them build a more comprehensive map. Experiments show that knowing parts of the terrain between home and a distant site improves navigation, suggesting that birds can extrapolate information from familiar areas to new locations. This dynamic updating ensures that birds remain efficient navigators throughout their lives. Avian navigational system is a marvel of flexibility and efficiency. Birds combine innate abilities with learned experiences to create a navigation system perfectly adapted to their environment. Sensitive periods in early life encourage learning, and specialized brain areas store navigational information. Regional differences in navigation reflect the unique experiences of each bird. The core of this system is compass orientation, which underpins both long-distance journeys and short-range movements. Whether crossing continents or finding a nest in an aviary, birds rely on directionally oriented mental maps, making them some of nature's most skilled travelers.